Have you all read that that paper for the drift diffusion model thing? Was that doable? Yeah,
When you say I read the entire one.
the entire one.
Yeah.
Ah, so now you're really very knowledgeable. So I thought the final part was just a bit too I don't know, too specific about specific experiments and that sort of thing. You agree? All right. Great. Yeah, so I'll go through that, your comments, your questions today. I'm hoping that Ron and Shifan have already been able to answer many of your questions, but I'll be getting into it today too.
Another part was measure information with the monkey experiment that we discussed in class last time.
Oh yeah,
So that was
nice. Yeah, sort of connected it nonetheless. Yeah. Well, so I appreciate your having read it, but I'm not going to force all the others to read it too.
I did a mistake.
Yeah. So this the dude that wrote this this Ratcliffe person, he's like this old dude that is yeah, is really the father of this field. So it's funny to see how he's going about this. Ooh, let's see.
So the diffusion model is also used right now, like most of them.
Yes, yes. So what you notice in behavioral research, and I haven't really gone into this much, but behavioral research in the past was often relatively simplistic in that people would just record reaction times for a given task. So you just look at the reaction time and then you just take like the average reaction time. People can do statistics on the difference between conditions or difference between groups of people, that sort of thing. And what you notice is that most of the behavioral research that people do is starting to incorporate this sort of modeling, really to try to sort of understand the mechanisms behind things more than just, some measure. Like we talked about, like accuracy, percentage correct, being some data, right? But it's not necessarily a reflection of the process that you're interested in. And similarly, if you use a drift diffusion model, you can really start to say things that are much more about the mechanisms behind the decision-making process, if you will, and not just focus on whether a t-test on reaction times is significant, sort of thing. Of course, this is sort of helped by these two different streams of sort of evolutions in the field. The one is that people are wanting to get at these mechanisms more because they're measuring brain activations more, like we saw, for example, in the monkey example, right? Where you look at really like spike trains of single units, but also people doing like MEG or fMRI experiments. They really want to get at this handle of a mechanism because, then like we saw last time, you can start to look for that mechanism in the brain also, and just the reaction time effect, very non-specific in terms of what you might find in the brain. But if you have a handle on a mechanism, then you can start to find it in the brain somewhere, right? Regardless of what type of measurement you do. And the other is also that doing and we'll talk about that perhaps later today, perhaps later on in the course, but to actually understand what's going on to get at this mechanism, you need to do things like model fitting. And that can be relatively complicated to set up by yourself if you don't have prior training or anything like that. And so with this whole open science thing that's happening, right? So people are more and more focused on doing open science. One of the aspects is that people are producing open source software that researchers can use. And that has lowered the threshold for people to start doing this sort of modeling themselves. So if you have just a random experiment, it becomes very easy with just a few lines of code to start, fitting these variables, fitting these parameters, and thereby being able to get at that neural level, get at that mechanistic level. And so there's a few things that help people start use it more and more. And if you now go into especially the sort of high profile journals, you start reading them, a lot, if not all of the sort of behavioral studies that do something with the brain next to it, they all use this model, this sort of decision-making model. It's not always a drift diffusion type model, but people use reinforcement learning models, that sort of thing. But this modeling aspect has become much more important in neuroscience in general. So you see this happening more and more. Yeah, and that's also, I hope, what you'll sort of get from this course, right? Knowing a bit of the ins and outs of how you sort of apply computational models to neuroscience might help you, also read the literature and get a handle on what the current state of the field is. Because it's much more than just, pressing play on a scanner or, on an MEG machine. There's a lot of thinking involved, using computational models. Oh yeah. Thanks, Marton. Thanks. It's excellent. There's Zoom messages. We've talked about how people make decisions, right? And we've started from the simplest possible decisions, and we've moved to these more complicated decisions in which a decision takes more time, right? And you are exposed to the sensory evidence of the task for longer, and then that necessitates you accumulating information. So that's one way in which the process of making a decision can be made more complicated. And this is also something that you'll see coming back in this course over and over, is that we start out with a very, very elementary model, a very simple model. And then once we see how that works and we understand a bit better what's the mechanisms behind that are, we can start adding specific dimensions. And we'll see that in this first part of the course, where we're really talking about modeling behavior. And we'll also see it in subsequent parts of the course, where we're really focused on more like explaining neural data. But in all these cases, you start out with a very, very simple model, and you want it to be as parsimonious as possible. And then you start building it up. We've seen this element of reaction times for these sequential sampling models. So today I want to talk about one other extension of this very simple signal detection theory model, and that is that of reinforcement learning. So the idea is, in reinforcement learning, you're also making decisions, but we're adding another factor here. So instead of adding the time that it takes to make a decision, what we're going to add is this element of time, but over trials. That is, you learning what the right decision is. And this is really something that we do in everyday life also. So what I'll do now is give you this lecture. Then I want to briefly show you the practical that will focus on these three different topics: signal detection theory, the sequential sampling, drift diffusion type models, and reinforcement learning. And then we'll see whether we have some more time. I'll try to explain a bit about model fitting. I don't think I'll be able to manage during today's lecture, but at least I'll be able to give you some sort of background for that. Okay? So this reinforcement learning, it centers on the idea that not all decisions are sensory. So up until now, we've spoken about these sensory decisions, and I've sort of alluded to the fact that we can also look at memory-guided decisions, for example. But if you think of a decision always being something where you judge one quantity relative to the other, we've always been looking up until now at this very simple sort of is this thing going to the left or the right, or do I remember this, yes or no? And these very, very simple decisions that you can think of as sensory decisions. And we've sort of expanded this into the realm of time, being time during a trial, right? You take more time to make your decision. Okay? But in many cases, the decisions that you make are not about whether you remember something or whether you see something or hear something, but they're more about what you want. So they're not about objective things in the world or in the past, like in memory, but they are about things that are subjective, things that you find valuable. And so this leads to a specific branch of decision making, which is value-based decision making. Now, this has a lot to do and has a lot in common with these previous types of decision making. And so there are very, very standard ways of also putting together these different types of models, the sequential sampling model and value-based decision making models. But today we'll be talking specifically about this value-based decision making. And we'll be thinking of this sort of framework where we're still always trying to remember back this sort of signal detection theory type framework, right? We have these probabilistic distributions, and we need to make a decision between these two quantities, whether what our choice will be. The question here is, though, if you're doing value-based decision making, if it's subjective, where does this value come from? And it turns out that this is like a very, very large branch of neuroscience. Also, how do we learn value? It's a beautiful branch of AI, of course, reinforcement learning, because we need to learn this value from the past. So whenever we make a decision on value, this value comes from something that we have experienced in the past. And so that means that we won't just be looking at time within a trial, but we have to think back to what happened in the past during our experiment over trial. So it's a longer history that we're going to take into account now. So who of you, so this is AI, of course, who of you have had full courses on reinforcement learning? Great. So you're all naive and I can tell you whatever I like. So what we're going to be focused on today in this specific lecture is this field of AI and field of neuroscience that is all about reinforcement learning. So that is, how do we learn value? You have making decisions based on value. We call that value-based decision making. The process that gives us this value, by which we learn these values, we call that reinforcement learning. So we learn by reinforcement. Yeah, it's not like you're learning how to reinforce a building or anything. You're learning through a reinforcement process. You learn through feedback. So I'm showing you this diagram here because this is the way that in AI we think about reinforcement learning. So in the field of AI, where we try to teach machines to learn from repeated experience, this is really the standard schedule that people look at. So in this field of AI, you want to set up a sort of artificial agent, and it needs to learn to behave in a specific environment. And so its goal is to maximize its rewards. Yeah. So the idea is here that you have an agent and it lives in an environment. It can take actions in the environment, and it does so based on its sensations that tell it what state the world and the agent are in, and it receives feedback from the world in terms of rewards. So those are the ingredients that we use to create this artificial reinforcement learning, artificial intelligence reinforcement learning. So what the agent needs to do is sort of estimate what state the world is in, and also have an idea of what states it wants to be in. Yeah? So what states in the world maximize its reward. And it needs to take actions in this world, depending on what state the world is in right now, and what future states are nice to have for this agent. Now, the main goal here is to maximize reward. As an agent, you want to do the best you can, and in this case, you want to learn how to maximize reward. And there are many different ways of sort of filling in this schema. But so different AI methodologies use different ways of filling this in. I'll talk about a few of them, but we're going to keep it really, really basic. What's important to realize is that all of these sort of really hip things that you may have seen, this AlphaZero type thing where the Google AI people teach a system, an AI system to play Go, for example. The main machine behind that is something according to this architecture, this main architecture. So what this, in the case of this AlphaZero, have you seen that documentary? It's a really nice documentary about this Korean world champion that gets totally crushed by the Google AI that's just way better than the world champion. I'll try to see if I can find the link and post it in an announcement. It's really nice. So so this is like one of the main parts of that type of AI. And what that in that case, of course, what you have is you have an agent playing another agent, right? Because it's a one-by-one game. And so you can simulate this entire thing. And the idea for that sort of training is that you let the computer play itself over and over. And you can do it really fast. So it learns from millions and millions of games that it plays against itself, and thereby becomes the best in the world. Now, that's one way in which you can look at reinforcement learning. That's from the AI lens of things. We can also take the tack of psychology. And in that case, it's really like, how has nature solved this, right? And how does that impact our minds? That gives you a totally different viewpoint on what this reinforcement learning is, because what you're focused on most in terms of which question you're trying to answer is not like, how do we optimize a machine and make it perfect, right? That sort of thing. That's an engineering type task. But what we're interested in terms of psychology and applying reinforcement learning to neuroscience is really, how do humans, or well, if you're doing like animal research, animals learn from reward. And then, of course, what you want to do is go into the brain and find the mechanisms responsible for us being able to learn from rewards. But in order to do that, of course, we want to have a model, right? Otherwise, I wouldn't be teaching it. So today, what I'll be talking about is how do we construct these models that allow us to understand how humans do this. Now, the interest here is not just in terms of sort of basic science. It's really interesting, like how do we learn or feedback. But in psychology, this has all sorts of applications. You can imagine that learning from rewards is completely broken in addiction. Right? You're not learning from rewards anymore, but the rewards are just overtaking you. Like your whole brain is set up into a different mode. It would be great if we can model this type of machinery and then find a model where we can change the settings such that we can have an addicted model, for example. And so that's really the type of use case that we want to go towards. Specifically, we also find specific things wrong in Parkinson's, and I'll show you an example of that today also at the end of the lecture. Things in OCD, like obsessive compulsive disorder. You have these very, very important because they hit a lot of people. A lot of people suffer from these disorders. You have these very, very specific things that you can find out if you try to understand the mechanisms behind this using this type of reinforcement learning model. Is that clear? Excellent. So what I'm going to do today in this lecture is I'm going to focus on these basic mechanisms, the basic algorithms that people have found out since the 60s, 70s on how to model this. So very basic models. If you look at the Google AI type thing, people are like light years ahead. But that's also losing its sort of application to psychology and neuroscience, because it really is like a tour de force of AI. So we could go into that, but that wouldn't really be what this course is about. So our goal here is to focus on the more basic algorithms. I'll try to outline how they work. And then, of course, I'll also try to show you how we've seen reflections of these algorithms, reflections of these mechanisms in the human and animal brain. So I'm going to do exactly the same thing that I did with the drift diffusion model. I'm going to try to show you what the underlying mechanisms are, how we model this type of a thing that we think might be happening in the brain, and then see how we can find it in the brain. Again, showing you how the use of these models helps us understand how the brain works. So specifically, we're going to try to use reinforcement learning really as a model for cognitive processes. But there are these two distinct things here that I want to separate a bit, because it's important to realize that they are two different components of the same type of behavior. When you have a system that does this sort of thing where it takes an action depending on the state of an environment and receives a reward and then does it over and over and over again, like we do, right? When we wake up in the morning and we start taking actions in the world, and the world gives us feedback, and we go on and on. Okay. So there's two elements here that we're interested in. The first is decision making, and that looks really similar to what we've already shown, or what we've already been looking at, the drift diffusion models and that sort of thing. And then there's a separate component, which is the learning. Yeah, the things that you've experienced in the past that now give you the values on which you base your decision. And this can go really broadly, but it's important to sort of separate these two different types of mechanisms. One really is about the learning from the reward, and the decision-making really is about how you decide which action to take. So they sort of occupy different parts of this loop between the agent and the environment. And when we start out with this, we're going to start out as simple as possible, and we're going to take out all of the action things. So we're first going to focus more on the learning, and we're going to not look at the agent's interaction with the environment. I'm going to take it really from the basics. We're going to start with the simplest type of reinforcement learning and then slowly build it up. So the first thing that we're going to start out with is classical conditioning. That's not even from the 60s or 70s. I think Pavlov was like in the 1890s or something. I was forgetting. Really bad with the years. So this is the sort of standard schema of the Pavlovian experiment. You all know this, right? Pavlov's dog. Who of you have actually had classes on this? Excellent. So many of you haven't, right? So cool. Just checking, right? So you have Pavlov's dog here, and before you do any conditioning, the dog likes food. That's what dogs do. So whenever the dog is confronted with food, it will salivate, right? It will go like food. Now, it's important to realize that we always use these specific abbreviations. US stands for unconditioned stimulus. Right? So that is a stimulus that is a positive stimulus regardless of any conditioning that goes on. Okay? We also have the UR, which is an unconditioned response. Okay? So that in this case is the salivation. Okay? That's sort of the baseline situation that we work with because dogs like food. Okay? And before we do any conditioning, we also have just a stimulus that we are going to try to sort of tie into this sort of reward thing that we already have. We call that a neutral stimulus. And a neutral stimulus by itself will not produce any salivation. So there will not be any response to just the tone, because the tone is completely separate from the food, right? The dog likes food, but the tone is like, yeah, whatever. That's our baseline situation. Now, the goal is for this classical conditioning, or the thing that Pavlov found out, is that if you tie the sound to the food, right, so if you tie the neutral stimulus in some way to the unconditioned stimulus, it will start to gain some of the positive sort of sentiment of that unconditioned stimulus. So that connection is being drawn by the process of the conditioning. So you're conditioning a response on another stimulus being present. Now, this is classical because the dog doesn't need to do anything. It's classical because the dog is just exposed to this and it will learn. Yeah? That's why we're also we're taking out that part, that action part of that schema that I showed you. It's really the passive learning of a conditioned response. So what happens when we pair the neutral stimulus to the unconditioned stimulus? We still get, of course, this salivation because there's food. We still get this salivation, but somehow the dog picks up on this congruency, right? There's always a neutral stimulus and an unconditioned stimulus, which then means that when you present the tone by itself, that will also produce a salivation response, right? So what this learning process does, it by tying the tone to the food, you're taking that neutral stimulus and you're creating a conditioned stimulus. So that's the process that happens here. What used to be a neutral stimulus now starts to gain some value in terms of its link with that food and the food response. So it's very, very simple. Everybody knows this, right? But it's pretty miraculous when they found this out, of course, right? They didn't really know anything about how this type of learning happens, and this was an accidental finding by Pavlov. The idea, again, being that we now have a conditioned stimulus and a conditioned response. So in terms of the classical conditioning, I'll just repeat myself, right? The classical conditioning does not require anything in terms of an action by the agent, just the exposure. Now, subsequent research has shown that classical conditioning is actually quite a complicated thing. It's not just this sort of 2x2 thing that we see here. It's much, much more intricate. And there are all these beautiful sort of dependencies that you can evoke if you make the experiment just a bit more complicated, a bit more complex. And so there's a few of these things that you can do that that show you that the learning process involved isn't just, oh, there's this link between the two and that's it. So the top row here is exactly the same sort of diagram as we just saw with the dog, right? So now we have a light bulb and cheese, which mice like, it seems. And in this case, so this is the mouse thinking something is going to be good. Apparently mice don't salivate. So you tie the light with the cheese, and in this case, after conditioning, the light by itself will produce the mouse thinking it's going to get something, right? So that's the acquisition. But there are these two other things that happen that show you that this is not the simplest of possible things. What you can do is you can go through this entire acquisition phase that we show here, right? So this is just a duplicate of the top row on the left, there in the middle row. If you keep doing this, if you keep showing that light and not reinforcing that light's connection to the cheese, what you'll get is extinction of the conditioning. So we call that extinction because it extinguishes that conditioned response over time. And so you also, so next to this sort of learning thing that we just saw with the dog or mouse will also unlearn things. We call that extinction. We also have this thing where if we've already conditioned a mouse to with a light, so the light is now attached to the cheese, it turns out that when you then put an extra sound on top of it, so not just the light, but you add another sound, it turns out that the sound itself is not conditioned on the food, right? So it seems as if you're already conditioned to link the light to the cheese, you're not going to, on top of that, also link the sound to the cheese. We call this Kalman blocking, right? So once something is already conditioned, you cannot sort of double condition. So any future conditioning is being blocked here. Now, it's important to realize that this is a very, very, very general thing. This type of mechanism and these signatures of conditioning, they don't just happen with mice and cheese. They happen all over the place. And the idea is classical conditioning just happens all the time. And it, for example, also happens when people have PTSS, right? So you've encountered a situation that was very traumatic, and just the idea of the situation or something that re-evokes the situation for you will give you this enormous stress response as a result. So you have some stimulus that triggers an enormous stress response. And that can, in that case, the unconditioned response is the stress response, right? And the conditioned stimulus is that thing that makes you relive the trauma. Yeah, and what that means is one of the things that that you then get is that when people do a therapy for PTSS, we call that extinction. You try to extinguish that link between the sort of cue and the stress response. Yeah, so that sort of dissolution of the conditioning also happens during PTSS treatments. So a very, very general principle. I might have to run out at some point to get some water. So that's all beautiful, right? These are some situations. This is all just examples. Yeah.
Yes, yes.
Sorry, post-traumatic stress syndrome. Yeah. So like Iraq veterans. Yeah.
Because I did a disorder. PTSD.
Stress disorder. Is it PTSD? Oh yeah, PTSS is the Dutch. I'm sorry. Yeah, I'm too Dutch. Turns out. Yeah, PTSD. You're right. Yes. Yeah. So my girlfriend does PTSD treatments. So hence my being all in the Dutch vocabulary. But it's really a beautiful thing to see that. Well, not PTSD itself, right? But the idea that there's such a general principle causes, very different behaviors. Yeah.
When we were mixing the sound and the light, we keep doing it. It will not gradually become one stimuli, and then it will make the red make the face. So
Ooh, that's a good one. Yeah, that's a very, very good question. I think it might. Yeah. But it kind of depends because you'd have to like do some combination of extinction and double sort of double conditioning. So it wouldn't happen in this situation, but if you sort of do this, where the visual conditioned response is extinguished, then that leaves a bit of room for the sound to become conditioned. Yeah.
So there can never be two conditions with the same like.
Well, there can, if you had started out with the sound and the thing, right? So that's the idea. And what that, and I'll show you what that means, right? But intuitively, it means that you have a sort of reservoir of possible conditioning that you can fill up either with the sound or with the light, right? And it just happens to like which comes first and that sort of thing. What determines what exactly happens in terms of the conditioning. Yeah. But of course, this wouldn't be. Any other questions about this sort of phenomenology? Great. Because this is all very sort of Ridley, right? So this is like a bunch of stuff that happens, right? And how do we sort of order this sort of thing? Well, it turns out that if we go into the literature, we can actually find that there are very, very simple models that allow us to capture these types of responses. And I'll show you how this works, how this type of model works. And then you'll see how these different aspects, so that is the conditioning, the extinction, and also the blocking, how they would result from just this very, very simple model. And so again, with all of these models, I'm going to show you the mechanisms. I'm not going to go into the equations. I don't think they're that important for this part. But what is important is these concepts, right? So we're going to start this model from the concept of predictions. And those of you that have done seminar cognitive neuroscience, Helene's course, right? I think she has a whole part about predictive coding, right? Same thing. So in the case of reinforcement learning, it's a bit more basic. It isn't such a general theory, but the ideas behind are very, very similar. Yeah? So we start out with the fact that predictions are paramount. The idea is that if you are an agent or a human being, your goal is to be able to predict whatever will happen, right? You want to be able to predict whenever some reward will happen or whenever some punishment will happen. Right? And here you see also that I'm just interchangeably using reward and punishment. Yeah. And that will become clear in a bit, and I'll highlight why that is. This also means that the sort of fuel for a learning process in a reinforcement learning scheme is that of prediction errors. And those of you that you've seen this in the seminar cognitive neuroscience course, right? A prediction error is something where you get a feedback from the environment and you didn't fully predict it. And so any difference between your prediction and the input is a prediction error. And you immediately see that a prediction error, it can be large if you didn't expect anything, right? Or you expected something completely different. So that will give you a large prediction error. One other thing that you notice here is that a prediction error should be able to be positive and negative, right? If you expect something neutral and something bad happens, we call that a negative prediction error. If you expect something neutral and something positive happens, you have a positive prediction error. Yeah? So there's also a sign to a prediction error. So what I'll be focusing on in my first explanation is just single valued, so single sign prediction errors, but things go both ways, and I'll highlight that later on. So the idea is that whenever you experience a feedback as an agent, as a human being, as an animal, what you get is some reward. You register something that you get. And internally, what you had was a prediction for what this reward would be. And of course, then a prediction error, which we call delta in many cases, and I'll adhere to the delta nomenclature. It's the difference between the expected and the actual reward. And here you can already see that it can be both negative and positive, right? That difference can produce a negative number or a positive number. So in this very, very simple reinforcement learning model, we're following this rule. It's called the delta rule because we call this prediction error delta. It's the difference, right? And the difference is usually called delta in mathematics. And we're going to say, this is just a very, very simple equation. I'm going to run you through it piece by piece. Right, so what we want to know is how much should an agent learn on every trial when you receive feedback? And that's that delta V, where the V stands for value. Yeah? So that's the difference in value that you experience on a given trial, or that you learn on a given trial. Now, the other thing is here the sum of value. So that's our present expectation of value, the expected value for this given trial. And what that, of course, is it's the sort of a condensation of everything that we've learned up until this point. The entire experiment up until this point gives us an expectation. On this trial, I'm going to get 80 cents or something, right? So that number here, it's now specified by a sigma. That's anything that you've learned up until now. Now then, we have this value of the feedback. We call that lambda, because if you fully predict what will happen, that means that your value estimate will be lambda. So that's the asymptote of your learning, right? So if you have zero prediction error, what you learned is that your feedback will be lambda. That will make this entire thing zero. And that's our delta, the thing that that I showed you just now, right? I've just interchanged the signs, but that's that delta. So we call that the prediction error. Now, then we put some multipliers before, like in front of that prediction error. And of course, what they do is they multiply how much you learn from a given prediction error. Yeah? And you can put things there like a salience of a stimulus, right? If you have a very salient stimulus, if you notice that stimulus really strongly, then you might learn more strongly from it. Okay? But a more foundational sort of parameter, we call that alpha, which is the learning rate. Yeah. And those of you that have trained neural networks, and this is, I'm sort of giving this away right now, but those of you that have trained neural networks, like using PyTorch or TensorFlow or whatever, the training algorithm also has this parameter in it, the learning rate, because in essence, what you do in many cases where you fit a model or you train a neural network model, what you're doing is something similar to this rule. You're using this delta rule in many cases. So This is really something that I want you to take away from this. So I'll keep repeating this over and over when we encounter this during the course. This type of learning rule we use in many, many different instances, and it is really the backbone of fitting models, understanding how models work, training neural networks, and understanding how agents learn from their surroundings and the feedback that the surroundings give. So, what happens when we go through a bunch of trials? Now, that's what we want to know. This is that dog. It learns to salivate when it hears the tone. The mouse learns to do whatever it did with its face when the cheese appeared, right? When the sound or when the light went on. So if this lambda has a value of 1, we'll keep it very simple, right? So that means that we need to learn the value of 1. Perfect learning means you expect 1 and no prediction error occurs anymore. You start out with this sigma v being 0. So whenever you get this feedback, you start learning, you take a step, and you move towards that value that you want to learn. And this is the way many different things work. What you're seeing here is an exponential growth function. Yeah. So this is really the standard sort of trajectory that this type of learning goes through. And if I want to learn different values in the end, so if my lambda has a different value, it's higher, what changes is not necessarily the shape of this curve, but what changes is the asymptote at which it stops, to which it goes to, well, this asymptote. And so if you have a lambda 2, that's the value of 2 instead of 1, you see that you get larger steps, but you could scale this entire curve down and it would be identical. So the speed at which you learn is exactly the same. It's just that the level towards which you learn that changes. What you can also do, so that was that parameter here in this model. And we're starting to notice, like now we have parameters in a model, similar to how we had a criterion and a sensitivity, V prime, in the signal detection theory model. Those are parameters, right? We also had like a drift rate and that sort of parameters in the drift diffusion model. Here we're looking at parameters of the reinforcement learning model. So we have that lambda, which is the asymptote, how much value do you need to learn? And here we're changing the alpha value. And here you see that the actual shape of that curve changes. So we're keeping lambda, the asymptote, the same, but this one has a larger alpha value and this one has a smaller alpha value. Okay? This makes sense because on every step, right, so you register some prediction error, that's the same at this trial 0, yeah? Because you expected 0, you got 1, so the prediction error is 1. But your step size is determined by anything that's multiplied with that prediction error, and that in this case is that alpha. Yeah? So the step size that you get, or there's different ways of saying this, it's the time scale of this exponential process. All of those are determined by that thing that you put in front, that learning rate. Yeah? So the higher the learning rate, the faster you learn. That makes sense, right? If you think of it as a learning rate. Great. So from the same model, from this same very, very simple equation, if you then say, okay, I've learned up to a value of 1. So I know the surroundings, right? When I press this button or whenever that light comes on, that's when I get food. Okay? So and the food is a value of 1. Well, if then that light does come on, but you don't get the food, hey, you expected 1 and you got 0, right? So at that point, what you get is a negative prediction error. It just flipped sign because the feedback just flipped in its flipped what it was. And at that point, you get this extinction curve, which is exactly the same curve because the learning rate is the same. But now it is an extinction process instead of a learning process. Yeah? So with this very, very simple idea, okay, we're going to register these prediction errors. We make this very, very simple model, right? So you shouldn't think of beta. I just put that there for completeness, but you only have a learning rate and your asymptote. Those are the important parameters here. And that's it. Yeah, you just take this little equation, you apply it step by step on every trial, and you can model the learning. And to get back to your question, like the K-min blocking thing, right? You can imagine that if you have learned up until this point, you're already at 1, right? And that at that point, I start putting in the sound, right? Well, the sound doesn't actually allow you to predict anything more because you're already predicting the entire feedback, right? There is no prediction error that the brain could be using to, tie the sound to the result. Okay? But only when you're already going down, that's why I said only when you're already in a sort of extinction situation, then you would have room to learn. Right? Then your brain would be able to start tying the sound to a prediction error there. Yeah.
But the mind is not expecting the sound, and it comes and you were like, what is the sound? So it was not expecting the sound, and it's something came. So it might, I don't know. I still didn't get it.
Okay.
So there's like a limit that gets filled.
Yeah, exactly. So there's a reservoir of sort of prediction error, right? That if it's full, you're predicting everything, right? There is 0 prediction error left, right? At that point, there's no reason to learn anymore because according to the model, the only full driving factor of the learning process is having these prediction errors in the first place. Okay? So if there's no prediction error, nothing to learn. Right? There's no, if this is 0, I don't care what alpha is, what your change will be, your learning is nothing. Okay? And so if everything is already predicted by the visual stimulus, I can put in the auditory stimulus, but it won't do anything more. That's the idea. Okay?
Also, this incoming of predictive music as a student, this is because it has got nothing to do with this prediction model, that it doesn't have any.
Yeah, so the model is pretty like agnostic, right? We could have started with the sound and then added the light. In that case, the sound would have been the thing that predicted the reward, right? And adding the visual stimulus, adding the light, wouldn't have added anything. Like there would be no learning of the light. Yeah. So it's not about the audition versus vision at all, right? It's just about which was learned first, right? Because what the brain did was to tie that prediction error to the stimulus, right? To audition or to vision, the one that came first, the one that was there when the prediction error happened. Yeah, does that clarify things?
And is it, sorry.
Go ahead.
Now, I wanted to ask, is it in the slides before for the conditional classical conditioning, you mentioned that there is a neutral stimuli and there is a condition that's combined. Then we are basically then combining both, right?
Yes.
So is it why we are not focusing on one neutral stimuli and one conditional stimuli?
Yeah, so the neutral stimulus becomes the conditioned stimulus. Right?
Yes,
Yeah.
but if, at the very initial stage already, if we include instead of one, if we do 2 neutral
yes.
stimuli.
Yeah, that's a nice question. Yeah. So then the brain has to decide, okay, where did this prediction error come from? Was it tied to the sound or tied to the vision, right?
Yeah.
And it's free to decide. It can decide whichever way it likes, in principle. Yeah. But of course, they might not happen always at the same time, always having to distribute the prediction errors 50-50, right? And then the brain would be optimal if it would decide on more audition. That's I'm learning the audition more now. That's also partly what the salience of a stimulus is. Like if you have a preference for audition versus vision, that would increase the learning rate, or something akin to the learning rate for audition and not for vision, and you would learn more faster for audition in that case.
Okay.
So if you like, so when the rat is completely certain that the light means food, for him to learn that the sound also means food, he needs to be less certain that light means food so that he can.
Exactly, because you need to have this thing, like you have to have this prediction error. Otherwise, there's no learning, right? The model is very simple in what it stipulates. It's just that you need this prediction error, otherwise, no learning.
But it always gets to 1, or it's not like it gets to 1, or it's never like.
Well, it's an asymptote, so it will never reach 1.
Yeah,
It
never
will
reach 1.
right? Yeah,
I never
and
certain.
and things are noisy, right? So
Yeah.
on one trial, it'll be less certain than another, and in real life, everything is always much more murky. But you had a question.
Yeah, it was related to her question, but it's like, it was related to the silence of the stimulus. Because it can be that one is stronger, that is more like, yeah, stronger than the other. So you reach one faster, and then there is no time for the next.
Yes. So they
The
compete.
other.
Yeah. So
value.
in a situation like this, they will compete, right? And then it's the one that learns fastest that wins, right? And so this type of equation, this type of process is a fully general one, right? So this is the same equation holds in a continuous way when you charge a battery, for example, right? It's when you fill a condenser up with a voltage. Like all of those type, it's a very standard type of process that you see here. It's like an exponential process. Yeah. And that was coming out of nowhere. I'll be with you. That was coming out of nowhere. So it's something similar when you have two competing exponentially growing processes. One wins and the other doesn't. It's why this happens in epidemiology also. We saw this in the corona epidemic, right? Corona epidemics also are exponential processes, and they follow exactly the same types of rules. So all of this is like a general sort of law of nature type of thing. Okay, that was out there, but yeah, you get the point. It's like a general principle, and it's applied in many different arenas. Yeah.
But if you want to condition the sound as well, wouldn't you just train them separately so that you have multiple stimulus that elicit the same result?
You could, yeah. Because if there's no light bulb allowing the mouse to predict that there will be cheese, right? Then at that point, there's unexpected cheese. There is a prediction error, and so if there's sound at that moment, it needs to learn from the sound. Yeah, so you can do that, definitely. So there's not a fixed reservoir, if you will. It depends really on the predictability. And that's really the crux here. We're always working from prediction errors. Yeah. You see how this sort of works, right? Let's have a brief break, 7 minutes. We can start back at 14:30. And yeah, we'll take it from there. Oh, wait. I saw a lot of, sorry, I missed these. Yes, very much like gradient descent. I'll be talking about fitting, and it's the same thing. Yes. Yeah, so, but indeed, like Martin said, it would be gradient descent in a static fitness landscape. Yeah, but in the delta rule is exactly the same. So the driving force isn't about prediction in time, but it is about this delta rule. I'll talk about that more either later today or in the recorded lecture that you can find on YouTube. Where am I? Yeah, I'm going to slowly restart because I have so much to tell you. We do need to finish in time.
Before you start, sorry to interrupt.
No, please, like in general, please interrupt me whenever you can. Right? Just find excuses to interrupt me. Yeah.
So, I actually asked you the question, then we have, what if we have two neural stimuli? So you said the brain will decide which one to prioritize, but based on what?
Yes, so things like is the animal paying attention to the auditory stimulus more or the visual stimulus more, right? That would be that data, like the salience,
Yeah.
right? And that would mean that you have two of these processes running simultaneously, right? And the brain is distributed, which of the two learning processes gets to soak up the prediction error. Yeah, so, but in any case of a human being, for example, you have many different reasons to believe that something that happened was caused by one immediate stimulus rather than another, right? You know, it could be your prejudice against some person, or it could be your, you know, just you know, you don't like I don't like bitter taste, or you know, anything where you just are confronted with multiple stimuli and you need to decide which one is the source of the prediction error, right? And this in a human situation in real life, this is evidently incredibly complicated, right? And so if you look at what people are doing now, and I used to have a paper in there, so there's this, so this is all shallow reinforcement learning, the things that we're talking about here. There's also deep reinforcement learning, which people use, and then this whole front end of deciding which stimulus we should be learning from is actually a deep neural network, like a deep convolutional neural network. So that then takes the task of you know, deciding which of the elements in the stimulus are the things that you need to be learning from. And so in the case of this, like the game playing AI, you have this entire neural network that's just devoted to understanding the game, right? In case of chess, like what is the king, what's the queen, what's the rook, what's the, so all of that needs to be done before you go into the actual reinforcement learning part. Does that?
Yeah, and can we then say that in case of human beings that we then decide based on our past experience?
Yes.
Okay, then it's value based.
Yes. Okay. So, yeah, so you have to see this happening at many different time scales at the same time, right? As a baby, you've learned that food is good, right? And sweet foods are better than bitter foods, sort of thing, right? And then all of the rest is built on top of that. And so, yeah, there's there's different elements to this that you can sort of extrapolate into everyday life. I'll try to sort of, you know, pinpoint them whenever we go through them. But I should at that point do it right now, because that would be messy. But yeah, it's this, and so you're pointing at a sort of fundamental tension that we have whenever we use models, computational models, to explain what is going on, right? And so that is, we're trying to keep things as simple as possible, right? But the real world is incredibly complicated. Yes. So you're never going to succeed when you're building a model, because the world is always going to one-up you in terms of it's being too complicated to actually model well. Okay? But there is this tension there where what we need to do is find the simplest model that will explain the most. This principle that I'll go into a bit later of parsimony, right? You want a parsimonious solution. Okay? You want something to be as complicated as necessary to explain something, but not a smidgen more. Right? It should not be more complicated than however complicated it needs to be. So it should be as simple as possible. Yeah, the world is a complicated place.
Yeah, you know, because we have the examples with animals, but yeah, well, I don't know. I couldn't actually no, I just wanted to understand how it works with us, because it may not be true how it works with animals works the same way for us. Human beings.
Yeah, so there are definite differences, and there's all sorts of, you know, cultural things layered on top in terms of human behavior. But like these basic mechanisms, they are very, very similar among animal species. So whenever humans are different from animals, it's mostly because we have something built on top that allows us to negate the lower level of the machine. That's in general the way that's what humans work. Well, this is a lovely conversation, but I'm supposed to teach. We just started out, and so it's the same thing as with the whole decision-making thing, right? We started out with the simplest possible model, and then we added ingredients on top, right? And now we have the simplest possible model in terms of reinforcement learning, But it turns out there's still problems, of course, because things are more complicated. Yeah, this was very, very topical discussion, actually. So there are things that we refer to as higher order conditioning that this Rescorla-Wagner model cannot explain. So the crux of this problem is that this simplest of models, it only predicts immediate rewards, right? And this is all as if the light and the cheese happen at exactly the same time, and that's it. Nothing further, right? That's the whole temporal extent of the entire situation, is them coinciding and your brain having to like link the two. That's it. Yeah. But it turns out you can put like a huge delay between the bell and the food. You can ring the bell, right? And a minute later do the food, and over time the dog will learn, right? But then this model, it doesn't work anymore, right? So this type of higher order conditioning, where you again add time in the mix, is problematic for a simple model like this. Yeah. So again, you see, simple model does beautiful things, right? It can replicate the type of behavior that we're interested in a very fundamental way, and then it breaks down because of some complication. And it turns out that when you want to extend this, you need to add time again to the model. And in theoretical terms, what that means is you need to predict all possible future rewards. Now that sounds very, very complicated, but in essence, in the way that we implement it, it's a bit more elementary than this. This sounds like you need God to do it or something like that, right? But not necessarily. And the way to extend this Rescorla-Wagner model to also predict future rewards is by a strategy we call temporal difference learning. So I'll briefly explain this temporal difference learning algorithm, and then show you how that would work in a brain. That's the idea. Okay. So when you show a reward predicting stimulus, in this case, a beautiful fractal pattern, that's pretty, isn't it? And after like I don't know, some time, you get a reward. Somehow the brain has to learn, hey, but this reward predicting stimulus, it will be followed by some reward. And then the idea behind temporal difference learning is that what your brain needs to do, or what an agent needs to do, or what this algorithm tries to implement, is that by virtue of this predictability between the reward predicting stimulus and the reward, the value of the reward is transferred onto the reward predicting stimulus. So we have a transferal of value from the unconditioned stimulus, that inherently pleasurable thing, to the stimulus that allows the organism or the agent to predict that said reward. And that's that value that gets transferred. Yeah. And what that means is that we need to have like a Rescorla-Wagner model for all manners of delay. Yeah. And that's also why this is called a temporal difference learning. So what we do is we have a bookkeeping timetable, like something happened at time t is 0, something happened at time t is 1, something happened at time t is 2, and we keep these active until at some point in time, we get a reward, and we see which of these things that are still active we should transfer that reward to. So this still works with the delta rule in terms of predictability, but now what you're basing this predictability on is not just a simple co-occurrence like you did in the Rescorla-Wagner model, but you have this entire temporal lookup table that you use to create this prediction. That's the basic idea, and the idea is that you're allowing this value to then be projected back onto these reward predicting stimuli that you're keeping track of in this bookkeeping table. And it's not just time that you're projecting back into. Yeah? You could also project back into states in the world, right? So you could have separate bookkeeping for times in the past, for when you're in a red room versus when you're in a blue room, right? Because the light might only need reward 10 seconds after the light, only in a red room and not in a blue room, for example. Yeah. So this lookup table is a very versatile thing, and we can use that lookup table construct to create really a model of the world in terms of how it predicts reward. Yeah. So this is that that extension of the Rescorla-Wagner model, and if you look at the equations that people use for that, you have again this previous estimate. You get a learning rate, so you have the difference there. So this is all is essentially exactly the same equation that we saw before. Yeah, you're still looking at a difference. Yeah. But you have this sort of discounted lookup table thing happening in the middle. Okay. I won't squish you about the specifics of this equation, of course. I'm not too interested in that. But this bookkeeping happens in this part of the equation where you keep track of how you could predict things, right? The things that allow you to predict are part of this lookup table, and we call that an eligibility trace.
How would this work in a continuous time, like in real life, where it just keeps going and going?
Yeah. So in general, the first models just did it iteratively because it's easier, right? You don't need as much memory and that sort of thing instead of continuous time. In experiments, also we have in many cases discrete trials, right? And then we don't have to keep track of time. But yes, this is all in continuous time. And then you can keep track of continuous time in different ways. There are people that think that what you're doing is instead of having like a discrete eligibility trace timetable, what you would have is like a sort of a beautiful sort of exponential curve for very recent, and then a bit slightly more stretched for less recent, and then step further, so that you have a range of timescales that you can represent by a sort of continuous. Well, we might call that something like a filter bank or something like that. So you're able to represent different time intervals by some combination of these things that extend further and further in time. And they are more precise when you're closer to the actual like time zero right now, and they are less precise if you go further into the past. Yes. Is that clear? So again, I'm not going to quiz you on exactly what's in this thing. The idea is here you have this lookup table. We call that an eligibility trace, and that allows you to have more complicated predictions of what might be going on. Yeah, and it means that you need to sort of fill in this eligibility trace because it's your estimate of what will produce value in the world. Yeah? So if values happen at this specific delay in the world, this specific delay after the stimulus, then you will get this to be a very valuable time point, and all the others will not. So the essential aspects of this algorithm, I won't go into this. This was developed in the 80s in terms of the AI part behind this. You can teach a model like this to play backgammon really well. That's what it's the sort of showcase scenario in which that people used for temporal difference learning was to teach it how to play backgammon. And if you were to take a reinforcement learning course, then your second week would be implementing a temporal difference learning model and teaching it to play backgammon. We won't do that, but that's the type of thing that you can allow this sort of thing to do. So basic games you can start playing with this type of model. But we're interested here in how these principles can be applied to the brain. And can we find reflections of this type of process in the brain? And so in the, what was it, like 99 or something, people, so a researcher in, I think it was Switzerland that time, was recording from this, what people also refer to as the pleasure center of the brain. So this person was doing like learning tasks in monkeys and was recording these single unit recordings, right? So single cell activations from this pleasure center of the brain. And that would be a reasonable thing to do, right? You're looking at the pleasure center of the brain and you're giving the monkeys rewards. So, and they're learning these rewards. So that makes sense. And you have these beautiful results and you have no clue what was going on. So this person then, as scientists do, they started talking to friends of his, and then they said like, oh, you should go to London. There's this dude who's been doing some computational work. He might be able to tell you more. And it turned out that these monkey findings mapped beautifully, but like more than beautifully, right onto this temporal difference learning mechanism. So how did that work? That was just the backdrop, right? This sort of pleasure center of the brain is called the ventral tegmental area. It's where these dopaminergic neurons are that project dopamine to the rest of the brain. That's why it's the pleasure center, right? It's also the, if you stimulate it, there's a lot of dopamine that flows to the rest of the brain, and a rat or like a monkey will go like, oh, and that's also what all drugs are sort of activate. That system is the pleasure center, the pleasure system. Yeah. The striatum is a specific region of the brain that's very much involved in developing actions, right? So if you experience something that's pleasurable, of course, you want to perform actions that give you that same pleasure again. Hence this specific strict coupling between these dopaminergic neurons and the striatum. So this is what that looks like. You have these dopamine neurons here on top of the brainstem, if you will, and they project their signals into the striatum and into the frontal cortex. So there's this link there. And so what this scientist that I was talking about, the monkey physiologist, had found is called Wolfram Schultz. What he had found is the following. So what I'm showing you here is single trial time courses of recordings of a single neuron, and you see its action potentials when it fires as dots here. If you have multiple trials, what you can do is you sort of collapse over the time axis over all the trials, and you end with like a baseline firing rate and then a peak in the firing rate. Yeah? That's what this sort of figure shows. And this is the situation in which the monkey doesn't have any information. The monkey's just sitting there fixating the center of a screen, and it gets a reward. What does a reward do? Well, the monkey registers that this reward is coming in and goes like, oh, right? And what happens is this response is part of that is that these dopamine neurons fire. Yeah, so you see this hump in the firing rate of these dopaminergic neurons. Yeah, that's this pleasure response that the monkey experiences. And now the goal of this temporal difference learning model, the tenet of the temporal difference learning model, is that if we have a reward that happens at some point in time, what this does is there's this eligibility trace, and it wants to project that value back in time. Yeah. So if there is a stimulus that allows the monkey to predict a reward, then the value should be transferred onto that reward predicting stimulus. So that's the idea of this algorithm. And so what this Wolfram Schultz had found was that if you have a reward at this time, but there was a reward predicting conditioned stimulus right before it, it turned out that these neurons all fired just after the conditioned stimulus. And the actual reward, the actual juice reward that the monkey received, it didn't give the monkey any reward response anymore. Because, yeah, it was fully predicted. There was no prediction error anymore at that moment. Because, yeah, I already knew this. I'd seen the beautiful fractal already. I don't know if we're using a fractal, but you get the point. Right. So this is a fully predicted reward. There is no prediction error. And we say no dopaminergic activation in this specific region of the brain, but there is a lot of activation when we see that conditioned stimulus. Okay? And sort of proof of the proof of the pudding is in the eating, they say, right? So what you then need to show is that when you don't give a reward, what happens then? Well, you expect a reward, right? So withholding the reward when it's fully expected, it should give you a yes, you get disappointed. But that's a prediction error, right? And what type of prediction error is it? A negative. Exactly. Yeah, so if this response is a positive prediction error because it was an unpredicted reward, you'd expect that a negative prediction error might do the opposite, right? And if you look at these responses, there's actually room for that. There's a baseline firing rate. So in the case where you predict a reward, the monkey goes, reward's coming, come on, bring it on. And at the point where it expects the reward, right? You see the disappointment in the brainstem of the monkey, right? I think that's beautiful, right? Yeah.
So they saw it because there was less dopamine.
Yeah, so every spike here, it transmits dopamine into the rest of the brain, right? So it means that the frontal cortex and the striatum, they will all be like, I need to do this more, whatever it is. Yeah? And that's also why we think that this prediction error through dopamine really is the driving force behind much of the learning that we do. It might be very complicated learning that you need frontal cortex for. It might be very elementary learning. It's just a simple action that could be striatum. But all of this is driven by that dopaminergic prediction error response. So this really is one of the foundational findings of basic neuroscience in the last 25 years. Well, it's almost 25 years old now. But this idea that you have very clear patterns of data. This dude had this, right? He'd been running around with this finding for I don't know how long, and he didn't understand what the hell was going on until he found this computational neuroscientist that was like, "You're looking at temporal difference learning, man. What else is new?" And so here you see also the power of having a model to explain pretty complicated patterns of data. Right? If you have this model, you have a pretty magical tool to understand, in this case, what the brain is doing. And again, it's a beautiful way in which this basic AI mechanism overlaps with what the brain is doing, right? So if you go from first principles and just think deeply about how the learning system should work, well, it turns out that the brain needed to solve the same problem, and it's used similar mechanisms to do so. Okay, so yeah, very beautiful results. Really like one of the trademark things in the field. Let's see. Yes, SARSA, very much like SARSA. SARSA is a SARSA is a specific reinforcement learning model that actually has action in the mix, and I'm adding action now, and I'm going to talk about a specific model that is more similar to SARSA. Very good point. And yes, the pleasure center of the brain is the nucleus accumbens. So it's this whole sort of set of regions of two questions here, right? The one was about the SARSA thing, and the other is about the nucleus accumbens. So the nucleus accumbens is the region in the striatum where these dopaminergic neurons transmit their dopamine to. So they're actually part of the same axis, and you could have recorded from the nucleus accumbens and found exactly the same thing, because the dopamine just arrives there, and you also get all sorts of firing, right? So they are really part of the same circuit. Yeah. I hope that clarifies things. So up until now, all of this has been passive. Yeah, all of this can happen without any action, just keeping track of states in the world passively. So what I'm going to talk about now is like the full diagram here, the full model where we do have action in there. I'm going to talk about this specific model called Q-learning, and it is very similar to SARSA in that it adds this action to the mix, and whenever you need to perform an action, you need to decide which action to perform. So instead of just having a learning mechanism, which we've talked about until now, we now will also have a decision-making mechanism, because we need to decide what action to take. And what that means is we're going to take all of those things that we've talked about before in terms of the decision-making mechanisms, and they now get folded into the reinforcement learning part. Yeah. So now we're looking at, instead of sensory decision-making or memory-based decision-making, we're looking at value-based decision-making. Yeah. So indeed, there are these models that fold everything together. You get this, reward learning part, and it has a drift diffusion model in it. Those very elaborate models go beyond what I can tell you in this course, but people are using those. They work well, and they are really important for this field, which is called computational psychiatry. And so this is really starting up this field with these types of behavioral models. People can start to understand the different mechanisms that go wrong in specific disorders, like addiction, like Parkinson's, like whatever. Okay, so by combining this reinforcement learning with this decision making, you get a nice view on what different mechanisms might play a role. And so what I'm going to do is show you a very specific instance where we in the lab conducted an experiment that we needed a Q-learning model to explain. Yeah, so I'm going to show you what this experiment is. I'm going to show you some results and highlight why we need this Q-learning model to explain the data. Okay. Now, this specific experiment is also what you'll be seeing in the practical. So the final part of the first practical actually is set up in a notebook where you simulate the experiment that I will be explaining to you. Because you simulate it, you actually have full insight into how value evolves in this agent that you're simulating. So it's an example of a reinforcement learning simulation. Okay, it's a very simple experiment because the world is complicated enough, and you want to constrain your experiment to be as simple as possible so that you can really zoom into the mechanisms that you're of interest. So in this experiment, people have to learn something very, very simple. They have to learn what colors they like. What that means is you have a learning phase in which people learn. They just sit in front of a computer screen. They fixate the center of the screen. They wouldn't even need to necessarily. They are then confronted with two stimuli, these two colored squares on either side of where they're looking, and they need to just choose. So they have two buttons on the keyboard. They choose one of the two colors, right or left, and they can appear like left, right, or right, left, like they can appear on either side. And they're always paired like this. So they're always paired, these two colors together. All your task is you choose which of the two you like best, and the experiment then tells you, or it tells you bing, bing, right? And well, you get what the two sounds mean. So you either correct or incorrect. Now, when are you correct? Well, that's a bit complicated. So let me get into that. You have 3 pairs. So there are 6 colors in total. And during this learning phase, we always show them in pairs. So you're learning everything in a set of 2. Now, these pairs are all more or less equivalent, but they're also different. And they are different in terms of the reward probabilities that go with each of the colors in the pair. Now, you can imagine that, so what that means is a reward probability is if you choose the correct one, what is the probability that you get to hear the bonus sound, right? That you get to hear the correct sound when you get a reward. So this is the easy pair, and A is the highly rewarded stimulus of the two. If you choose it, you get a reward in 80% of the time, 80% of the occasions. Okay? You still get in 20% of the cases, right? But the world is random, so this makes sense. We're used to learning stuff in random situations. Okay? On the other hand, if you choose the blue one in this case, B, you get in 80% of the cases, you get right, and you only get a reward in 20% of the cases. So that's not so confusing. If you do this 2 or 3 times, right? That's easy. But these pairs are different because we change these percentages around, and as you go to E and F, which is code letters for these different colors in this case, here it becomes really, really hard, right? If you do 4 trials of this, they're equal, and you still have no idea what it is, right? So you need to do like 20, 30 trials before you know which of these two is the highly rewarded one. So what we would expect is that you learn this one really fast, this one intermediate, and this one really, really slowly. Now, that's cool, right? Because then you can actually see, you can imagine that if someone learns really fast, you have this parameter that you're interested in, namely the learning rate. It's a parameter, like a very fundamental parameter of this type of learning process. And you actually have a measurement of it. You can just look at the percentage, correct, that people are responding, and you see how fast they are learning. So that's beautiful. So we have a lot of measurements, like behavioral choice measurements. And we also have this second phase, which we call the transfer phase, in which we shuffle up the pairs. In which case, there's a separate thing that you can learn from an experiment like this. For example, in this case, you're pairing 60% with 30%. There's a 30% difference, right? But it turns out that people are, and this is beside the point, I won't really go into this during the lecture, but some people are very good at learning from positive feedback. Other people are very focused on negative feedbacks. And it turns out that if you have, for example, you can pair the 20% and the 30% with one another, they're 10% apart, right? So the difficulty would be the same as pairing 70% and 80% with one another, right? But people that learn from mistakes much more strongly than from their successes, they'd be really good at 20 versus 30, because that's a situation where you only get negative feedback, right? Whereas the 70-80 one, equally difficult, 10% difference, just on the other side of the spectrum, you've got a lot of rewards for that. So some people are driven by all these positive feedbacks, and they are much better when you juxtapose A and C versus B and D. Okay? Well, that's an aside. I won't go into that anymore. But you see how like a very, very simple experiment, you just shuffle specific things up. You think deeply about the effects that you're trying to get at, and you can get like very, very insightful results from a very, very simple experiment. Now, we didn't think of this experiment. This was thought of by a very smart person, and he did this in Parkinson's patients and during medication of Parkinson's patients. A couple of science papers, also, very, very beautiful findings. So it turns out that for an experiment like this, you can use a relatively simple model still. So it's really in that same family of Rescorla-Wagner reinforcement learning models and the temporal difference learning model, and the SARSA model for the ones that are interested in that. So this Q learning model, where Q is similar to V, but it's in an action context, so then we call it Q. The idea is that now we have two different stages in this cycle where the agent interacts with its environment. It's different from what we had before. So we don't just have reward learning, we also have this decision making. And the end, so you go through this action sequence during the experiment, right? You choose, you get feedback, choose, get feedback, choose, get feedback. And so the end, what you want is a good Q table, this lookup table where your values are stored. Yeah? So what does that look like? Well, I'm plotting you here Q, so this value of a specific stimulus, and you see that you learn this value over time. You see exactly this sort of exponential increase of the value of a stimulus over time, and you keep learning that. This is the not chosen stimulus, right? So it has a lower value, and the other one is the one that you choose. It's always above the red, more or less always above the red one. And so you see here also the randomness of an experiment like this. Sometimes you get like feedback that goes against what you should be learning, that sort of thing. And so it looks really noisy, but you definitely see this thing where you get this learning process, right? There's a specific rate at which this person is learning from the positive feedback. Now, I already spoke to you about these two specific aspects of this Q learning model, right? Because we've added action in the mix, we have decision-making and learning. And it turns out that this type of model really has this beautiful separation of these two ingredients. So you have one part of the model that is like a trait. And what that means is that it is a fixed characteristic of a single agent or observer or actor. And again, I won't quiz you on the equation, but the idea is that this separates people into people that like to explore and people that like to exploit. So what does it mean when you explore? It means you're random, right? You just go like, whatever I know, I'm just going to try stuff out. Yeah, that's exploration. Now, exploration stands for a low beta in this. So beta is one of the parameters in the model, and it makes a very shallow decision-making curve. So you can think of this as a, it's similar to like a D prime sort of thing, right? If this is a very shallow line, your D prime is low, which means that you make random choices of y. Because here is that difference in value, and this is what you end up deciding. If you're very random, it doesn't matter so much what the difference in value is. They're just going to be, very random. You can have a very, very large difference in value. You need to choose one of the two, right? And still you're only at 80%. So in 20% of the cases, you're making the wrong call. Means you're kind of a random person. You explore around amongst the options a lot. You can also be an exploitative person. What that means is you have your value estimate, and that can vary along the same axis as for that other observer that I was just talking about. But you have a very, very steep curve. That means that you have a very high beta weight or beta parameter in this model. What that means is only a slight variation in the difference in value that you've learned, you're going to decide the one that's the highest value. So you are always going to base your choices on the thing that you know, right? And so based on that thing that you know in terms of your learning, that Q difference, you're going to exploit that knowledge. So that makes you an exploitative person. And you can see this sort of map onto different types of personalities already. I'm sort of intuiting that you might. And your intuitions are probably correct. So people differ in this sense. It's a trait. Some people are very explorative, other people are very exploitative. So this is a way of trying to measure a functional characteristic of an agent. But it's all about the decision-making part of this process. It takes as a given this difference in value. So the learning process is separate. That just gives you an input onto this axis, and then this random curve gives you what people might decide. The other side of this, so this is the same sort of explore exploit. So in a fixed experiment like this, this is how that would work. It would be a trait. You can have other experiments. So I'm segueing into a different type of experiment, to be clear, right? I'm not talking about the experiment that I'm introducing here. You can have a different type of experiment where you have 4 different slot machines and their payoffs change over time, right? So total shouldn't put a gambling addict in this type of experiment at all. But people they pull this slot machine and they find out I get a lot of reward. Okay, I'm going to stay with that one, right? And then they'll notice that the reward starts to decrease. So then they're going to pick something else, right? And so you're going to be like switching from slot machine to slot machine to try to get the highest reward during the experiment. Okay? Now, in that case, every choice that you make, you could say is an exploratory choice or an exploitative choice, right? So this sort of exploitation thing is not just something that's a trait in which people differ from individual to individual, but there's also an explore-exploit trade-off for any behavior that is in a changing world. But that's a segue. That changing world thing is a definite segue. We call this task a multi-armed bandit task. So feel free to forget about that. It's just so that you know that this explore-exploit trade-off happens not just between individuals, that they differ in that sense, but you also see it over time. Right? In life, you get this. Or am I going to gamble, or am I going to stick with what I know? We all know this sort of conundrum, this sort of choice that we need to make. So then there's this other Q-learning model component, and you already know which one it is. It's the learning. That's very similar to what we've already seen. We just have this learning rate here, and in this case, we have a model that actually allows us to see whether people learn from positive versus negative rewards. Remember I said that, right? Positive versus negative. Some people are focused on negative, other people are focused on positive. And so that means that for this model, we have 2 different learning rates. One is for gains and the other is for losses. Turns out you have this experiment, and you can actually have these 2 parameters that allow you to quantify how sort of negatively driven or positively driven an individual is. Now, of course, the alpha, I already pointed out how the value sort of evolves. You see this exponential rise. And now completely similar to what I showed you before with after Skorla-Wagner model, right? You see this sort of slow rise. You have a low alpha, so the learning rate is low. And you have a very high alpha, it goes up immediately. And you also see how people differ in terms of learning rates in a more general sense. If your environment is very volatile, right, and you need to, and you know that things only slowly change in the environment, it helps to have a low alpha because you need to integrate more information, right? Similar to the drift diffusion model, sequential sampling, right? If things are hard, you want to take more time to integrate information, and a low alpha actually allows you to integrate more information. So there's a nice sort of parallel between the reinforcement learning and the drift diffusion model. And of course, if you have a high alpha and you have a very fluctuating environment, you're going to go all over the place. Right? You're going to, like a dog running after squirrels. That's what your brain would be doing. Okay, bad analogy, but you get the point. And you have these reward prediction errors, right? For every choice, you get a feedback, and that's really the prediction error that drives the learning. Yeah. And so these are the ingredients of that learning part of the model. You have these prediction errors; they happen on every trial based on what you've chosen, and you have these variations in how people learn. And it turns out that these things are very, very different in terms of people will vary in terms of their learning rates. They will also vary in terms of their explore-exploit biases. And this really allows us to model their behavior and then sort of qualify what type of person am I looking at. Yeah. Is this person exploitative? Is this person learning fast from positive versus negative rewards? You get this sort of compression of the individual into a very, very sensible and interpretable parameter space, because all these parameters relate to how behavior evolves. Is that clear? Great. So, when you do this sort of experiment, like I just said, right, this quantifies the differences between observers, and you can really sort of see what type of behavior someone is developing. Allows you to really say you're that type of person. In a couple of different ways, in a multidimensional way. And so we've done this in Parkinson's patients because Parkinson's patients have this problem with dopaminergic signaling in the brain. Fireworks over there. Anyway, but this lecture is always also fireworks, right? So. So the Parkinson's patients have a problem in the substantia nigra, which is also a very, very prominent dopaminergic center in the brain. It's less a pleasure center and more like an action development center, but it is also dopaminergic. And the cells in the substantia nigra, they die off, which means that the dopaminergic signaling in the brain decreases. Right? And there's some overlap between this reinforcement learning type of dopaminergic transmission and action generation dopaminergic transmission. So the idea would be then that we can find shifts in how Parkinson's patients behave when they are on versus off medication. And so we can better try to understand how their behavior changes. It turns out that you can do this, right? So you have these quantifications of the parameters for each of your subjects. You compare them to healthy controls, and you have your Parkinson's disease patients off medication and on medication. And that then gives you a shift about like what does the adding dopamine to the brain do in these patients, right? And we can also compare then this effect of the medication to an effect of the disease in general. Yeah? So comparing them with healthy controls. That's the idea there. And it turns out that Parkinson's disease changes two of these specific parameters. One having to do with the decision-making process, and the other having to do with the learning process. Now, the learning rate that it changes is the loss learning rate. So the being focused on negative rewards, that's changed. You see that there's a very strong shift in the learning rate for that alpha loss, which is the learning rate for receiving a loss. where it is lower in Parkinson's disease in general. And there's also a slight effect there for the explore-exploit tendency, but not so large. What you then see is that the dopaminergic medication really changes this alpha loss effect. It has an effect on specifically this learning rate thing that the disease has changed. Okay? So to be clear, right? So the disease has a slight effect on the decision making, the explore-exploit tendency, and it has a larger effect on the how you learn from losses. And then supplementing the dopamine actually fixes this alpha loss problem, but it doesn't change so much the beta weight. So the dopaminergic medication only changes that learning rate. And so this really allows us to very specifically points these very specific. I just already said that, but properties of how a subject behaves, right? And if we give them medication, it changes how they learn from losses, but it doesn't change their explore-exploit tendency. But that explore-exploit tendency is changed when they become sick. Okay? So it shows us that what Parkinson's does in the brain and what dopamine does in the Parkinsonian brain are quite separate things. Right? They partially overlap, but not completely. And we were able to, for those of you that would be interested in how this works in the brain, all of this behavior was actually acquired in the scanner. And so we were able to also look at these dopaminergic parts of the striatum. And it turns out that you see this effect of these reward prediction activation. So that's that learning process element in the striatum. Do I need to go back? Do we want to go over that again? Or was that clear? All right, so the specific effect of the learning that's ameliorated by the medication, we actually see in the striatum. You can actually see this in the human brain in the striatum. Now, so what I've done up until now is really showing you these basic principles and how, in patients and in behavior, we can find evidence for these different types of model components. How you can understand the mechanisms behind this type of behavior, this type of reinforcement learning, by separating out these components, for example, the decision making and the learning. But in terms of present day AI, I just wanted to go back to that, right? We have this deep reinforcement learning, which marries the type of thing that we've talked about up until now that we are interested in terms of a clinical perspective, right? We use these types of specific computational models to understand what happens in specific patient populations, for example. And that can be combined with this classical deep learning. Right? Many of you will be familiar with that. We'll be talking about that in the next couple of lectures. Classical deep learning, convolutional neural networks, that sort of thing. How are they a model of the human brain? And so this would be like a front end that allows you to say, okay, I'm looking at a dog or a cat, right? I'm looking at a sound or a lamb, right? So a front end on which you need to base your reinforcement learning decisions. And if you marry these two, what you get is deep reinforcement learning. So you have this complicated thing that allows the network or the model to understand the world. And then you have this reinforcement learning part that allows it to develop and learn from its action by integrating the rewards from the environment. So you need these two different types of architecture. This one is a model of the sort of motivational areas of the brain, like the dopaminergic centers of the brain. And this one is a model of a more sensory part of the brain that we'll go into in later lectures. Right? So both of these ingredients are models of how the brain does something, but there are different parts of what the brain does. One is development of behavior and the other is more sensory. So what we're going to do is we're going to, after this, I won't immediately go into the sensory part of the brain and the deep convolutional neural networks much, but what we'll do is we're going to talk about how we fit models to data. So the next lecture that you'll see, that you can see online, is about how we fit these models to data. So if you're talking about these parameters, right, and how they tell you something about what type of person someone is, and what type of decision someone's making, but how do you get this quantification? Right? You have a bunch of choices. How do you get there? Right? And so there are a couple of lectures online that you can peruse these couple of the next week. And then when I come back, I'll be going into the remainder of the course. Oh, yeah, ik wil ook over tijd, sorry, excuse. Yeah, vanavond, yeah. So we're going to look at Bain routines, and then after that, we're going to look at deep neural networks. Yeah, sorry for taking so much time. Yeah.